Hey everyone, it's me, Miss B, and in this video we're looking at the Unit 4 Lesson 2 Cumulative Practice Problems for Illustrative Math Geometry. So this lesson was all about half of a square, which makes a special right triangle looking like this one over here on the right, meaning it has a 45-degree angle and it has a right angle, of course, because it's a right triangle. So for this question, the first question, we want to find the lengths of the legs. Now, we know that there is a ratio of all the side lengths here. Since this is a special type of right triangle, it's isosceles, since both of its legs are going to be the same. Um, now, we can use the Pythagorean theorem to actually find this, or we can use what we learned in class today, which is that we know each of these side lengths has a ratio with the hypotenuse. So we used S, but some of you may be more comfortable using X. But basically, we said that if one side is S and another side is S, then the ratio for all squares followed the pattern that the hypotenuse would be the same as S times the square root of 2. And I actually like using this to help guide me through finding pieces. So as long as I write all of those things on the sides, I can think to myself, okay, well, now if I'm finding the side lengths, I need to take this and I need to find just S. So I can set this equal here and say, okay, I need to find just S. And I can go ahead and start solving this equation. So we're going to solve for S. What would you do? Well, you would have to divide by the square root of 2 on both sides. I'm going to do this work here in blue. That way it stands out a little better. So we would divide by the square root of 2. And in that case, that would leave us with S. But then we have to simplify this 4 divided by the square root of 2 piece. Now, in order to do that, we actually can't divide by the square root of 2. We need to change this into a whole number. Now, normally, something that's inside of a square root, to get rid of that, you would just square it. In this case, we can't square the number on the top. But fortunately for us, squaring something is the same as multiplying it by itself. So we can still apply that principle, and we can multiply this by the square root of 2. That's the same thing as squaring it. And instead, we're then also going to multiply our numerator by the square root of 2, since we're not going to square the numerator. So when we simplify this, we end up with 4 times the square root of 2. And then if multiplying something by itself is the same as squaring, whenever you square something that's underneath a radical, specifically a square root radical, you end up with just that number. So it's almost like the square root sign effectively disappears here. Now, that's because this becomes the square root of 4, and the square root of 4 is 2, but I used to always think of it as just multiplying them with each other makes those square roots disappear and just leaves that number underneath. So I have 4 times the square root of 2 divided by 2. I can take this one step further, and I actually need to simplify, if possible, these two numbers right here. 4 divided by 2, I can do. And because this is a single term, it's not something plus another thing, it's just two pieces multiplied. We can reduce this entire thing and just call this and say that S is equal to 2 times the square root of 2. Now, if that was an odd number, like 5, we're actually not going to reduce that, and you can leave it as 5 times the square root of 2 divided by 2. But this one was a multiple choice question, actually. They gave us some things over here, and hey, look, that looks like one of my answers. And I did just find S, which I had said earlier was what the side was equal to. So if I'm saying that, I'm saying this is 2 times the square root of 2. And so my choice here should be B. which would make sense. Now, I did kind of lose my 4 in the middle of this here, so let's get that back. 4, I'll highlight it there. If we look at the rest of these options, we can see why they don't really make sense. 4 is the hypotenuse, so it needs to be the largest of the sides. It can't be the same, so I can't have my legs be 4 because that would make this an equilateral triangle and not a right triangle. It also can't be bigger. 4 times the square root of 2 is going to be bigger than 4, which means that the hypotenuse would not be the biggest side length, and that's impossible. So 2 times the square root of 2, if you're just trying to narrow things down, would be the only one that works, or not enough information, but there definitely is enough for us to solve it. But at least that would, give you a 50-50 shot at answering things correctly if you were just guessing, making an educated guess. But that brings us now to question 2. And this is a little bit more of the whole main idea of our lesson in class today, which is dealing with the diagonals of a square. So what is the length of the diagonal? Be sure to show your work. I'm just going to draw it in here so that you can see where I'm doing some things. Yay, straightened it out. Okay. Now, they are giving us one of the side lengths here as 1. And because this is a square, we know the other sides are all 1. And they want to know what is our hypotenuse. So I always like to label the hypotenuse as c because of the Pythagorean theorem. And that's how we're actually going to solve this. We are going to use a squared plus b squared equals c squared, because I could just say, oh yeah, I know my ratio, and that should just be 1 times the square root of 2. But we're going to show our work. And so if I'm trying to show someone why this works, we're going to use the Pythagorean theorem. So if I have a squared plus b squared equals c squared, c is always the hypotenuse. And I can just say, I don't know, just call each of these a and b. So 1 squared plus 1 squared is c squared. 1 squared is 1. So that becomes 1 plus 1, which means we have 2 equal to c squared. And I just want to find c. So our step here would then be to take the square root, which means the only thing left here would be c, and we cannot simplify the square root of 2, so our answer would just be that the diagonal is essentially 1 times the square root of 2. So question 3 takes this a little bit further. It's giving us the diameter, or I'm sorry, diameter, that's a circle. It's giving us the diagonal, and then it wants to know what's the area of the square. So let's actually draw ourselves a square. Maybe I'll make this blue. Hopefully this is square enough after my tablet turns it into one. Close enough for me. Okay. So I'm going to say, hey, this is a square. All the 4 corners and all the 4 sides. Got it. It has a diagonal. So I am a visual person. I like to draw all of my things so that I can understand them and see them better. So that diagonal right there is 5. Now, normally this would be the piece with the radical attached to it, but in this case it's not. So we actually need to find out what is the side length of this square. But first let's talk about the area. If each of my sides is S, area is length times width normally. And in terms of a square, that's going to be for us S times S, whatever that side length is. So my actual area that I'm looking for is going to be the same thing as if I had S squared. Now, this is a little bit tricky, but what I am going to show you is a version of the Pythagorean theorem where we actually don't solve just for S. But we can do this 2 different ways, so we'll show you both. but I like this way because it's kind of ingenious. We are just going to try to solve for s squared because they're not asking us what the side length is. They just want to know what's the area. So let's set up our Pythagorean theorem. I am going to have s squared plus s squared, and that is going to be equal to 5 squared, since 5 is the hypotenuse. Now, I can't do anything with my s squareds here. I can't actually square them because I don't know what the numbers are, but they are like terms. So I can actually add these together and say this is 2s squared, and that is equal to, and I can square the 5, and this becomes 25. So you'll remember, I am not solving for just s. I just want to solve for s squared. So in order to make just s squared, we just have to get rid of this 2. So all we're going to have to do here is on the left, just divide by 2, and it will cancel out, which means our answer is going to be whatever 25 divided by 2 is. And so s squared, this is actually the same as 12.5. And that would be our answer. Now I'm going to show you another way proving that this is actually correct in case you don't believe me or you maybe did stuff in class a little bit differently today. And you're like, Miss Bauman, but why is it like that? Well, we can continue. And if I said s squared is 12.5, or in this case, I can take the fact, like the same way we were kind of finding other pieces here in the first one, how I used a 4 and then I found the side length. I'm going to use that method. So if I know that 5, I'm going to actually draw a little line here because I'm going to separate my 2 methods. You only have to do one of these. If you're comfortable with the one I did over to the left, you can probably skip ahead to the next question. But I can say that I need to take s. In order to find s, this is going to be the same thing as whatever our side length was, divided by the square root of 2. So that means I have to multiply by the square root of 2 on both sides of the fraction, not of the equation. So the numerator and the denominator here. And that would give us 5 root 2 divided by 2. This is one of the side lengths. So if my area is the side times the side, what I'm going to do is actually 5 square root 2 over 2 times 5 square root of 2 over 2. That would give me 25 for the 5 times 5. Root 2 times root 2 is just going to give me 2, the same way we would rationalize that denominator. And then 2 times 2 is 4. So my area, if I simplified it out, I can cancel part of these things. I can either say that part of my 2 and 4 cancel, or we can just kind of multiply out some numbers here. I have less room than I thought, so I'm going to make a shorter arrow that maybe comes up. Well, not shorter, but give myself some more horizontal room. This is going to be, we can just say 50 divided by 4. That's the same thing as 25 divided by 2. And look at that, 25 divided by 2. And that gave me the 12.5. So yeah, your area would be 12.5. And since this is centimeters, we can even say centimeters squared. So you have 2 options. The way you might have thought about this first is this one, where you find what your side length is and then multiply it with itself. But there is also this method where we realize, hey, we are just looking for s squared. You can use the Pythagorean theorem to then find that. But that is question 3. The answer there is 12.5. Moving on to question 4, we have Priya, and Priya is teaching her younger cousin to ride a bike. She wants to stay on roads that are not too steep and that are easy enough for a new bike rider. So she's decided that roads have to have an angle less than or equal to 7 degrees. And they're going to tell us what a ratio would be for a 7-degree angle. So in a right triangle, the legs would have to have a 3 to a 25 ratio. And we want to list the legs of 2 right triangles that would be safe for a new bike rider. So I can draw myself similar to the ramp that we had in one of those other questions. And I don't know if this is actually going to be appropriately to scale, but I'm just drawing a triangle here to help me explain it. If this leg is 25, then this leg here would have to be 3, and that would give us a 3 to 25 ratio between the legs. Now, I can use any triangle that is similar to that, or I can make the 25 longer. If I made that side longer, that would actually create a smaller angle. So I can say, if I do 3 and 25, I can multiply those by any scale factor that I like, or I can say this could be like 3 to 30, which really would end up being like 1 to 10. But both of these technically work as long as the longer leg is the only piece that gets longer. It just can't be shorter, because if it gets shorter, then we end up with a much steeper hill. Likewise, we can't have our hill get taller, because then our hill gets steeper as well. And so this just said 2 right triangles, so I can say 3 and 25, and I can say 3 and 30, but we can also take 3 and 25 and just multiply those by a bunch of different scale factors. But that's the idea for number 4. So that brings us on to the back page, which is the last part of this assignment. Only a couple more questions to go, 5, 6, 7, and 7. So there's technically 2. You can consider this one if you want to change this so that it's 8. I'm going to change this so that it's an 8, and I'm going to call that question 8. Okay, let's look at question 5. Claire and Han are discussing how to find the missing links, and we have 2 triangles here. Claire says she's using similarity, and Han says he's using the Pythagorean theorem. Do you agree with either of them, and show or explain your reasoning? Well, since these are both right triangles, as long as we're only missing one side, yeah, we can use the Pythagorean theorem. And hey, I am only missing one side on this triangle, so the Pythagorean theorem will work. Same with this one, I'm only missing one side. Now, in order to use similarity, I need to know that the triangles are similar. But fortunately, we do have that these triangles are similar because they have angle-angle similarity. All right angles are congruent to each other because the definition is that it's 90 degrees. And they are giving me 2 angles here marked, and I'm just highlighting those blue. They're marked as congruent, so I know these have angle-angle similarity, so I agree with both. So I am going to say both could be right. Can be right. The triangles are similar by, I'm going to say angle similarity. They give us another variation of this question where we're supposed to like find one way and then find one another way and then check them the other direction. But yeah, we can find both of them this way. Now, if you haven't recognized it, this one right here is actually a Pythagorean triple. So that means it's going to come out to be a whole number. 5, we would normally have 12 and then 13, but I'll show the math to just prove to you that it works out. So I'll call this B, and I can say 5 squared plus B squared equals 13 squared. This is 25 plus B squared. And 13 squared, that is a very messy 2 that I put on there to the power of 2. This is 169. We're going to subtract 25 and subtract 25, and that would give you that b squared is 144. So go figure, it's going to be 12. So that would be this missing side length here. If you wanted to use similarity, we could use the scale factor of 1/2. 5, and in this case now 2.5, are in the same corresponding position on this triangle, so those leg lengths correspond. From our larger triangle, or from the 5, our pattern or our scale factor is 1/2 because we are dividing by 2. We can use that same pattern here to help us find the hypotenuse, which we're given on the larger triangle is 13. So I can say that this would be 13 over 2 or 6.5. So I'm going to just kind of circle here. I'll probably do this in red just to show my other method. Divide by 2. 13 divided by 2, or 6.5 would be our answer here. Okay. And that is my answer. Question 6, and then 7, and then 8. Okay, so we have a right triangle, ABC. C is the right angle, A is 25, and B is 24. What is the length of AC? Let me draw this triangle. All right, I'm very sorry about that. My recording cut out on me again as I was trying to actually draw this. So I'm drawing this triangle. C is the right angle. And then they're giving us two lengths. They're saying one of them is AB, and that's 25, and BC is 24. Well, since C is here, AB are the other 2 points, and that means these two, and so this is going to be AB. That's my hypotenuse. I want the 24 to be my other long side here, and that was BC. So I'm going to put B at the top here and have A. So my actual naming scheme goes A, B, C around the top like that. Now we can do the Pythagorean theorem to come up with what our answers should be. If you don't recognize it, it is going to be a whole number, and I guess you will just have to work with me through this one to see what it's going to end up as. I'll just use x here. So x squared, x is one of the legs. So x squared plus 24 squared is going to equal 25 squared. So 24 times 24, not equals to, plus is going to be 576. And 25 squared is going to be 625. So let's subtract that 576 from the 625, and you'll end up with x squared is 49. Now 49 is one of the answers, but we have to do the square root. So this is actually going to be 7. So our answer here is C. 2 more questions. We have some similar triangles here. We want to find the length of EF. Well, actually, they're not telling us they're similar, but I have a feeling. And then we want to find the measure of angle E. So if we zoom in here, we have one angle that is the same, that's the 55 degrees. And then we have we have an 82 and a 43. So let's take 180 if we subtract 55 from that, 180 minus, oh, this is a little too thick of a marker here. Get my thinner pen. 180. And if we subtract the 55, that's going to give us 125. So, that 125, we basically want to see if 82 and 43 make 125. Or in this case, I can just subtract the 82 to find what the missing angle is for angle C. So if I take this and now subtract 82, guess what? It is 43 degrees. 43. So they wanted us to find angle E, which means I need to go to my other one here. These I know are going to be similar now because 43 and 55 are two shared pieces. So there is angle-angle similarity. So I am going to write down that this should be 82, just to help me keep a frame of reference. Now they said the measure of angle E was one that I needed to find, and that was what I just wrote down as 82 degrees. So I am going to write 82 degrees as my answer for that part. And they wanted to find the length of EF, so I'm going to call that X, and we're going to solve for that. So, excuse me, 82 and 43, that is not my laser pointer. I wanted the laser pointer. X is between the 82 and the 43, and that lands here on this triangle. So X is going to correspond with the 12. We have 14 and 21 as our other numbers here. You can check those are in between the 55 and the 43. So those will correspond. So I am going to say, if I take 14 and I compare it to 21, that should be the same as if I took 12 and compared it to X. Sorry, my throat's bothering me a little this afternoon, apparently. So we are going to say 14 for this one here. 14 over 21 is the same as if we took 12 and then put that over X, right? Yeah, 12 over X. Make sure I use the same variable there. So you can try to reduce the one on the left first if you prefer, or you can just multiply it out and use a calculator. Either is valid. Now we can say 14x if we cross multiply, and then I'm just going to multiply 21 and 12 together, and that gives us 252. Last step here is to divide both sides by 14. And that is going to give us x is equal to 18. Or basically EF is going to be equal to 18. That's our answer. That means we have one more question here. And this one is possibly true, definitely is, or definitely is not. So we always have three options. It has to be, it could be, or it will never be. So we're going to determine these two statements and which of those applies. Isosceles triangles are similar. Not all isosceles triangles are similar. So the real question is now, can they be similar? And the answer to that is yes. So this is going to be could possibly, in terms of being true, because it doesn't have to be, because I could have an isosceles triangle that is like short like this, or a tall skinny one, and those are not necessarily going to be similar to each other just because two sides are the same. But equilateral triangles have to have all three sides the same. And I know that side similarity is um, it is one of the ways that we can prove things similar. So this one would has to be true, or they say must be. So let's use their wording. Must be true. And we also know that all equilateral triangles have angles of 60 degrees all around. All the sides are the same and all the angles are the same. And so these would all have angle similarity with each other. They would have to be true. And that's it for question 8. And that's going to be it for homework assignment 4-2, um, which is the Unit 4, Lesson 2, Cumulative Practice Problems for Illustrative Math Geometry.